Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss Fraunhofer diffraction at a single slit. Let's begin. In case of Fraunhofer diffraction, this type of diffraction that takes place at a slit when the source is at infinite distance from it. Fraunhofer take some assumptions to find out the diffraction pattern at a single slit. According to him, both the source and the screen are at infinite distance from the slit or obstacle. Here is the source, there will be the screen, this one be the obstacle, here we use the single slit, source and screen both are infinite distance. Also the slit, or we can say that is the obstacle, here we use a single slit, is at infinite distance from the source. Again, the wavefront incident on aperture, or we can say it as the slit, is a plane wavefront. If that source is a point source or cylindrical source, at a long distance, if we observe that wavefront, it is seen to be like a plane wavefront. So the incident wavefront or that of single slit is treated as the plane wavefront. Now we consider a monochromatic source of light S that emitting light waves having the wavelength, let lambda be the wavelength of light, of light source of monochromatic light source. Lambda. Now we use a convex lens L1 so the emitted light rays are incident on that of convex lens L1 So, the light rays are passing parallelly. A parallel beam of light, that is the wave front, is incident on that of narrow slit. That narrow slit is named as AB, having the width at D be the distance between these narrow slits. The width D placed perpendicular to the plane of this paper. Let the diffracted light is focused by another convex lens. Here we use another convex lens L2. The parallel light waves now converge to a point on the screen, that is O. That screen is placed the focal plane of the convex lens L2. That is why the parallel rays now focused at point O. Let that diffracted light is focused by that of convex lens L2 on the screen XY placed in the focal plane of that lens L2. The diffraction pattern obtained on that of screen consists of central bright band and having alternate dark and bright bands of decreasing intensity on both sides. Here, due to diffraction, here we observe the maximum intensity, then the intensity gradually decreases on both sides from O. That is known as the central bright fringe. Again, that point is the first minima, that is the first secondary minima. Next is the maxima, which is the first maxima, first secondary maxima, and so on it is named. Let we have to mathematically understand what be the position of central bright and the exact cause of that diffraction. Now, why that type of diffraction pattern we observe on that of screen. Let you prefer, here the light wave is diffracted at an angle theta. Due to theta angle of diffraction, let you take the observation point on that of screen be P point. these two light waves are superimposed at point P. In this way, due to theta angle of diffraction, we observe a diffraction pattern on that of point P. Now, what will be the diffraction pattern? Let we calculate the path difference in between these two rays which is diffracted at an angle theta from the 2 points as A and B. Let me draw a perpendicular from point A to that ray BP, that is K. So, BK is the path difference in between these two rays. So, the path difference between secondary waves according to Huygens principle, that be the secondary waves which is the cause of the disturbance of primary wavefront originating from points A and B in direction theta is equal to Bk, that is Bk is equal to that is the diffracted angle. So, that angle also equal to theta. From that up right angle triangle BKA, from right angled triangle ABK, sin of theta is equal to BK divided by AB. So, BK divided by AB is equal to width of that of slit small d. Therefore, BK is equal to d sin theta. So, BK is equal to d sin theta. That be the path difference between the secondary waves originating from the point A and B in the direction theta. Next, we have to calculate the phase difference. The corresponding phase difference the relation between phase difference and path difference, the phase difference is equal to 2 pi by lambda into path difference. 2 pi by lambda into path difference, that is d sin theta. Our aim is to find out what be the position of central right and first secondary minima, first secondary maxima, and so on. For that purpose, here for central right we obtain the maximum intensity gradually the intensity decreases. For maximum intensity, the resultant of amplitude must be maximum. First we calculate the resultant amplitude, then the relation between amplitude and intensity, we get the resultant intensity. To calculating the resultant amplitude, let the width of that of slit is divided into n equal parts. Let the width of the slit be divided into n equal parts. Why we take that one? Due to calculating the resultant amplitude. So, the amplitude of variation, at P due to the waves from each part will be same. Let us say that be the amplitude A. Since we take the slit is divided into n equal parts, so at point P the waves are starting from these slits having n number of equal halves. Let each wave having the amplitude same, which is equal to small a. So, the phase difference, if we prefer any two of the consecutive parts, so the phase difference will be how much? Then the phase difference between the waves from any two consecutive parts is phi is equal to, that be the phase difference divided by n due to n number of equal halves. So, 1 by n 2 pi by lambda d sin theta is the phase difference between any two consecutive parts. From that phase difference we can easily calculate the resultant amplitude. Hence, the resultant amplitude at P is given by, we know if there are a number of simple harmonic oscillations are perpendicular with each other, so the resultant amplitude can be calculated by the formula R is equal to each wave have the amplitude A sine of n phi by 2 divided by sine phi by 2. Here we use using the superposition of n waves, the superposition of n waves concept, or anybody can use the vector calculus also. If n number of vectors are acted simultaneously at a point having the successive angle, then the resultant can be evaluated by using that formula. Now put the values of phi here. We have the resultant amplitude at point P, r is equal to a sin n by 2 1 by n 2 pi by lambda d sin theta divided by sin pi d sin theta divided by n lambda. Now simplifying, we have r is equal to a sin pi d sin theta by lambda divided by sin pi d sin theta divided by n lambda. That is also a angle. Let we substitute. Let pi d sin theta by lambda is equal to a angle alpha. It's our substitution. Then the resultant amplitude r is equal to a sin alpha divided by sin alpha by n, sin alpha by n. Since alpha by n is small, since alpha by n is small, for n number of parts it is very small, therefore sin alpha by n for small angle it is nearly equal to alpha by n. Sin of very small angle, if we calculate sin of 1 degree, sin of 1.5 degree, it is almost same value. So sin of a small angle gives rise to that angle. Therefore r is equal to a sin alpha divided by alpha by n, or r is equal to n a sin alpha divided by alpha. As n tends to infinity for large number of equal halves, therefore the amplitude a tends to 0, but the product n a have a finite value, is finite. Therefore let we take the product n a as a. Therefore r is equal to a sin alpha divided by alpha, that be the resultant amplitude. By using that resultant amplitude we can easily calculate the resultant intensity, as we know the relation between resultant amplitude and resultant intensity. Therefore resultant intensity at point P being proportional square of amplitude, square of amplitude. The resultant intensity I is directly proportional the square of amplitude, resultant amplitude R square. Avoiding that proportional, we use a proportionality constant. So I is equal to K R square, where K is the constant of proportionality we taken K is equal to 1 or I is equal to R square. Value of R square is put here. So resultant intensity I is equal to A square sin alpha by alpha square. From that equation, from that of resultant intensity equation, we can easily calculate the position of central maxima and secondary maxima and minimas. Look at that figure. Here we get the central, right? Here the intensity is maximum. After that, intensity gradually decreases. At these points, intensity will be minimum. Here intensity maximum, at these points intensity minimum. Using that concept, the position of maximas and minimas can be calculated. So here we calculate the directions of maxima and minima, maximum and minimum, maximum and minimum. For principal maximum, for principal maximum, look at that of expression. For principal maximum, we have principal maximum or central maxima. Central maxima I is equal to infinity. Here highest intensity of light wave, that be at infinity. Therefore, put that value A square sin alpha by alpha square is equal to infinity. What be the exact condition to take I be at infinity? Here A will not equal to 0, not equal to 0. Then alpha is equal to 0. That is why alpha is equal to 0. To get maximum intensity, I is equal to infinity. We have alpha as we substitute lambda d sin theta, sorry, pi d sin theta by lambda, pi d sin theta by lambda is equal to 0. From that expression it is clear that sin theta is equal to 0 or theta is equal to 0. So the central maxima, the direction of central maxima is obtained when that theta is equal to 0 degree. When theta is equal to 0 degree, these parallel rays are coincide at point O. So at point O we have the central maximum, that be the direction of central maxima. This will occur at point O on the screen. At point O on the screen we have central maximum. Next, secondary minima. What will be the direction of secondary minima? Secondary minima. Again same condition, I will be 0. For minimum condition I is equal to 0, intensity will be 0. So intensity will be 0. Here we use the expression as a square sin alpha by alpha square is equal to 0. So amplitude not equal to 0 and alpha again not equal to 0. If alpha is equal to 0, then the intensity will be maximum. Therefore the term sin alpha must be equal to 0. So the value of alphas we have, where sin values are 0 for plus minus pi, plus minus 2 pi, alpha not equal to 0. Therefore we starting from pi, 2 pi, plus minus 3 pi and so on. Generally we use that is plus minus n pi. Here the values of alpha as pi d sin theta divided by lambda. Therefore d sin theta is equal to plus minus n lambda. Here pi cancel out, where n stands for 1, 2, 3, etc. And the d sin theta is equal to n lambda. That be the expression. This is the path difference. This one is the path difference, integral multiple of lambda. So path difference is equal to plus minus n lambda. When path difference is the integral multiple of lambda, that will be the condition for minima. From intensity concept we derive the condition for minima in terms of wavelength. Which gives the directions of first, second, third, etc. minimum. First secondary minima, second secondary minima and third secondary minima can be evaluated by using that equation as pi plus minus 2 pi plus minus 3 pi and so on. Next, how we get secondary maximum? Here is the central maximum, then the maximum we obtained is treated as the secondary maximum. Here the minimas are plus minus, means on either sides we have the minimas, one half for upper half, another for lower half. Next, secondary maximum, that one is important. What will be the direction of secondary maximum? To calculating that secondary maxima, we have to differentiate to find directions of secondary maximum intensity we differentiate equation of intensity I with respect to alpha and equate it to 0. Equate it to 0. Gradually the intensity decreases. Therefore, differentiating intensity with respect to alpha and equate it to 0, we have easily calculated the direction of secondary maximas. That is, let differentiating it. So d I by d alpha okay, d by d alpha, put the values of I, a square sin alpha by alpha square is equal to 0. Its differentiation, simple differentiation, a square as constant, that is outside, and it is in the terms of division in form of denominator and numerator form. Therefore, we use 2 sin alpha by alpha alpha cos alpha minus sin alpha divided by alpha square is equal to 0. Look that of expression, that term a square not equal to 0. 2 sin alpha by alpha, as alpha not equal to 0. Therefore, that term must be equal to 0. For alpha is equal to 0, we have maximum intensity. When that term again not equal to 0, so the term alpha cos alpha minus sin alpha divided by alpha square is equal to 0. Therefore, alpha cos alpha minus sin alpha is equal to 0, or alpha cos alpha is equal to sin alpha, or alpha is equal to sin alpha by cos alpha, which is equal to alpha is equal to tan alpha. Alpha is equal to tan alpha. So, what be the values of alpha here? To evaluating the values of alpha, we have to use two equations. Here I write that equation can be solved graphically by plotting. Let we have two equations. Let y is equal to alpha, one equation, and another equation y is equal to tan alpha. How we have to find out the curve? Let me prefer the graph as shown here. Just considering the positive halves. O x y. Here the values of alpha, here the values of y. To doing tan alpha, let we draw the lines. Here pi by 2, pi, 3 pi by 2, 2 pi, 5 pi by 2, 3 pi, like this. Again in the negative halves also the same thing. Now y is equal to alpha. What will be the curves looking like? Y is equal to alpha. If I compare the general equation of straight line, y is equal to mx plus c, where m is the slope of that curve and c is the x intersection. Comparing that equation, we have m is equal to 1 and c is equal to 0, means that straight line passes through the origin, and m is equal to 1 means tan theta is equal to 1. What value of tan theta is equal to 1? Tan 45 is equal to 1. So that line y is equal to alpha is a straight line and cuts the origin with an angle 45 degree. This is for positive halves. Again same thing for negative halves. If we draw the negative halves, then that straight line passing through this way. So y is equal to tan alpha. Tan value, tan values are considering the graph of tan values. Tan pi by 2, here is at infinity, here at infinity and then 0, 0 transform to infinity. This is the graph of tan. This is the graph of tan function. As we have already discussed in case of calculus 1 in mathematical physics paper 1, how to plot the graph of tangent function. Next thing happen here. So it records the graph in the points at point, let the intensity be I, here intensity I1, here intensity I2, intensity I3 and so on. So the values of tan, by solving equation this and that graphically, we have the intersection of two graphs gives the values of alpha which satisfying alpha is equal to 0, 3 pi by 2, 5 pi by 2, 7 pi by 2 and so on. Therefore we say alpha is equal to 2n plus 1 pi by 2, odd multiple of pi by 2, or alpha, which is lambda d, pi d sin theta by lambda is equal to 2n plus 1 pi by 2, pi cancel out. Therefore d sin theta is equal to 2n plus 1 lambda by 2. Again, if the path difference is odd multiple of lambda by 2, here is the path difference, odd multiple of lambda by 2, we have secondary maximas. These are the values of alpha that decide the directions of secondary maxima. Now, using these expressions, we can easily find out how the intensities are distributed for central maxima. Here for central, or we can say principal maxima, principal maximum, alpha is equal to 0, alpha is equal to 0 here. When alpha is equal to 0, the intensity I is equal to I0, which is equal to a square. From that of figure, we obtain the central maximum here. Next, for first secondary maximum, for first secondary maximum, alpha is equal to 3 pi by 2, alpha is equal to 3 pi by 2. So I1 is equal to a square sin 3 pi by 2 divided by 3 pi by 2 its square is equal to 4 a square divided by 9 pi square minus 1, which is equal to 4 a square divided by 9 pi square. Again, for secondary maximum, alpha is equal to 5 pi by 2, for secondary maximum, alpha is equal to 5 pi by 2. Therefore I2 is equal to a square sin 5 by 2 divided by 5 by 2 whole square. So we have 4 a square divided by 25 pi square, which is equal to into 1, sin value, sin of 5 by 2 is equal to 1. We have 4 a square divided by 25 pi square, and so on it carry forward. So the ratios of intensity, so the ratios of intensities. Here a square, 4 a square divided by 9 pi square. Therefore, ratios of intensity I, I1, I2 and so on is equal to the ratios. Here a square cancel out, we have 1 is to 4 by 9 pi square is to 4 divided by 25 pi square and so on. That will be the ratios of intensities. When we plot the graph in between the intensities, here the intensities and alpha like 0, plus pi, 2 pi, 3 pi, minus pi, minus 2 pi, minus 3 pi and so on. The maximum intensity here we obtain. This is the central maximum. Then now the intensity distribution, in Fraunhofer diffraction from a single slit is the minimum at alpha is equal to plus minus pi, plus minus 2 pi, plus minus 3 pi. Here is the minimum. The principal maxima at alpha is equal to 0 and secondary maximas at alpha is equal to 3 pi by 2, 5 pi by 2 and 7 pi by 2. These are plus minus. On either sides we have corresponding maximas and minimas. So these are the minima. You can say secondary minimas as first secondary minima, second secondary minima and so on. Principal maxima and secondary maxima, which are the secondary minimas. Okay. So with the help of this visual exercise we understand the Fraunhofer diffraction at a single slit. First we calculate the path difference, then phase difference, taking this slit in divided into n halves, any two consecutive halves, the phase difference, then the resultant amplitude. From that of concept of resultant amplitude, we calculate the resultant intensity by taking the superposition of n harmonic waves equation. Next, the directions of maximum and minimum. For principal maximum, intensity must be at infinity, therefore theta will be 0, that will be the position of central maximum. Then secondary minimum, intensity will be 0, that is the expression for minima. We say when the path difference is integral multiple of lambda, then we have minimum. Secondary maxima is calculated differentiating the intensity with respect to alpha. Alpha is equal to tan alpha, that can be solved by taking two equations, and graphically we solve the values of alphas are the odd multiple of pi by 2. From that of expression we have the path difference when odd multiple of lambda by 2, we have the value of maximas. Then that expression we have central maxima, first secondary maximum and second secondary maximum, the ratios of intensities, graphical view of distribution of intensities in Fraunhofer diffraction. From that of above conclusion we have the secondary minimum at these points, principal maxima at that point, and secondary maximum at these points. So with this useful and informative notes, let me wind up this session. Thank you.